So in class we practiced balancing these rulers with different weights on both sides. You can see there's 5 pennies to the left of my finger, only 1 to the right. And the other obvious difference is that the distance the 1 penny is much larger than the distance the 5 pennies are. We saw some patterns with that.
So here's some data from Southmore during the 2012-13 school year. Basically what they saw is they could have 2 pennies on the left if they kept them 6 inches away from the balance, and they could have 4 pennies on the right if they kept them 3 inches away from the balance. And the obvious thing here is that those products, number of pennies times distance, equals the same thing on both sides. Likewise, you could do 1 penny 6 inches away, you could do 6 pennies 1 inch. So this product is clearly something important.
So what we're going to look at now is how force and distance work together to introduce a new concept. And the new concept is basically a rotational version of force. If all of a sudden I started stacking extra pennies on the right there, we would expect a rotation. If I started stacking extra pennies on the left, we'd expect a rotation like that. And it turns out that these rotational forces act a lot like regular forces.
So let's refresh ourselves how regular forces add. Here's a person standing here. They have an upward normal force, a downward gravitational force. We can write sigma F equals ma. We call the upward force positive, the downward force negative. The acceleration is 0 in this case. So we can see that the forces are balanced. If you aren't accelerating, all your forces must balance. This new thing we're looking at is a lot like force. In the case of force, an upward force makes me accelerate upwards, a downward force makes me accelerate downwards. With this new idea,
these pennies are balanced because the rotational force to the right, or actually in this case clockwise, is balanced by the rotational force to the left, or in this case counterclockwise. We have a name for rotational force. We call it torque. So I want to try to come up with what the rules are for torques.
So when we go back to our data, we remember that it was the number of pennies on one side times the distance those pennies were from the balance point that appeared to have to be equal on both sides. So this product of pennies times distance must have some physics significance. Let's use some better terms for it. The number of pennies was a stand-in for weight, the weight of the penny. And we're going to call the distance from that force to the balance point the lever arm. I just have it labeled as D. We're going to call this product force times distance torque. It gets this symbol tau, which is a Greek letter. We usually use Greek letters for rotational quantities. And just like we had to have forces, in order to not rotate, we have to have balanced torques. So you could see that what we noticed, that the force times distance on both sides being equal, comes up with an equation that looks a lot like a sigma F equation. We see the torque in one direction minus the torque in another direction equals 0. So we actually have a new equation, sigma tau. And we're going to use this just like we used sigma F. This is our way of checking that rotational forces, or torques, are balanced. I just wanted to point out that we had a little bit of wiggle room in our lab because my finger was not infinitely thin and the penny was not infinitely thin. So we had some situations where sometimes the force and distance weren't perfectly balanced. But if we did use what's called a knife edge balance, and we could very precisely balance our weights at a single position, and very precisely balance the thing on a small pivot, then you have to be very, very close in order to get things to balance. If this was a little bit further, this thing would rotate clockwise. If it had been a little bit farther this way, it would rotate counterclockwise. So the next thing I want to do is explore this equation, force times distance equals torque, a little bit more. And I want to see if there's anything else that's important. After we do that, we'll go back to sigma tau having to be equal to 0 if something is balanced. And again, that's just like saying upward and downward forces must balance. We're going to be saying counterclockwise and clockwise torques must balance.
One of the best ways I know to talk about torque is to look at a doorknob like this. This doorknob has its axis of rotation here, and it's got a lever arm going out like this. So I'm going to apply forces at various distances and directions relative to this axis of rotation, which you can see with the keyhole. So if you use the doorknob the way it's designed, you need very little force. With my pinky, I can rotate it. I'm pushing straight down, or I'm pulling straight up.
So I've drawn a picture of the doorknob. I've got the axis of rotation here, and they've got the lever going this way. And we just checked out F1 and F2, and we saw that they were very small forces. I could do it with my pinky. So those are the forces that you're supposed to put on this doorknob, and you don't need very much in order to cause the necessary torque, either counterclockwise or clockwise, which I have labeled here. If you notice, these two forces have something in common. They're both acting as far away from the pivot point as possible. They have the largest D, or lever arm. And they're also perpendicular to the lever arm. Let's check out what happens when they're not perpendicular to the lever arm. Let's try applying F3.
Let's say I put a force parallel to the doorknob. I can hang on this, and it doesn't rotate at all. So forces parallel apparently don't help.
So F3 doesn't help at all. It's parallel to the lever arm. We're saying that that's the big difference between it and the two forces that worked really well. Let's check what happens with the force I have labeled F5 here, a force that's at an angle.
If I go at an angle, not straight up or down or not parallel, it's a little bit harder, but I can do it.
So I know in the video I put an F5 down like this, but just like F1 and F2 are equivalent, one having a counterclockwise torque, one having a clockwise torque, the two versions of F5 would be as well. So we'll use the one in the picture. We can see why this one required more force to make the door rotate. If we think about how F1 and F2 caused a torque and F3 didn't. If we look at F5, part of it is like F3, parallel to the lever arm and does nothing. Only the perpendicular versus the one like F1 or F2 does anything. So to find out what that perpendicular component is, we use sine, and therefore F sine theta is the force that actually helps us. That leads us to the torque equation not just being torque is Fd, which we've seen before, but torque is Fd sine theta. So what we'll see in all torque equations is that what causes the rotational version of force, torque, is how hard you're pushing, how far you are from the axis of rotation, and this trig component to make sure that only the part perpendicular to that lever arm is contributing to torque. Let's look at F4 and F6 just to make sure we understand the importance of lever arm, how far you are from the axis of rotation.
The other thing that's important is I can use my pinky to rotate here, but that doesn't work here. I need more of my hand the closer I get. And if I get really close, I have to push very hard. And if I'm right on the axis of rotation, it can support all my weight without rotating.
So what were we seeing there? Well, F4 had a smaller d, and therefore it needed a larger force to make up. So when this got smaller, that had to get bigger. F6 had a lever arm of 0. So no matter what times 0, we get no torque. It doesn't matter how big force is. So all three of these are important in calculating a torque.
Let's see how torques add and subtract. We're going to see it acts just like force in this regard. The big place you're going to use torque is very similar to how we used force. Not in calculating a single torque, but in looking at the net torque, or the sum of torque, sigma tau. So you do it very much like you did with sigma f. You figure out what all the torques are, and you add them up, and you get a result. A broad class of torque problem that we should know about are equilibrium problems, when the torques add to zero and stuff stays balanced. Let's look at a problem, and I apologize for the poor quality of this shot. It says a little kid who's playing on a pile of wood. They have a mass of 35 kilograms. She walks out on a plank that's 5 meters long and supported at one end and then partway down, 3.25 meters. The plank has a mass of 10 kilograms. How far can she walk before the plank tips? This is probably something most of us did as a kid, and we were surprised when it tipped on us. But basically, we have a pivot point here. And the only way that we're not going to fall is if the clockwise torque we put on it is balanced by some sort of counterclockwise torque. Just like the reason you don't fall out of your chair is because your weight is balanced by the normal force. So we'll use our understanding of forces to answer this torque problem. We write sigma torque equals 0, and we look at what the two possible torques are. There's the counterclockwise torque, or excuse me, the clockwise torque caused by the girl. So that would make this thing spin clockwise around this pivot point. And there's the counterclockwise torque, which is actually caused by the weight of the wood. As long as those two are equal, she's not going to fall. So it looks a lot like a sigma f equation. There's only one difference. It doesn't just have the f's, it also has the lever arms, which I have labeled R1 and R2. Notice R1 is the distance the girl is from the pivot point. R2 is the distance the center of mass of the board is from the pivot point, because the weight of the board we can assume acts at that location. So I just solve this around to have the two torques set equal to each other. I plug in all the numbers and I can figure out how far she can walk. If she goes less than that, she's fine. If she goes more than that, this equation can no longer be true and she'll start to tip. In some classes where I have enough class time, I have kids build mobiles. I have them go get 4 small objects like Happy Meal toys or anything else they can think of, and we hang them from sticks, and we balance the torques that are caused by the objects to make these cool mobiles that hang balanced even though we have very different amounts of weight on either end of the stick. These mobiles were made by my students at Southmore in 2015-2016. We then practice calculating what the masses and distances must be for this to stay balanced. I want to show you a calculation. So here's one such calculation, and the way you work with this is you always start on the bottom rung. So I said that we had one object massing half a kilo, one object massing a tenth of a kilo, and we were on a stick that was 0.3 meters long. So again, it's balanced, so the torques add to 0. That means the torque caused by the half a kilo minus the torque caused by the kilo must be 0. Notice I just subbed in the equation for force, F equals mg, for both torques. And then I started to solve. I used a little trick here. I don't know either of the two lever arms, but I do know the whole stick is 0.3. So I plugged in x for one of the lever arms and 0.3 minus x for the other. And then I was able to solve how far we had to place the larger object from the pivot point in order for it to balance. Then I could go back and find the other lever arm. Then you work your way up. This whole bottom rung becomes one of the objects on the next rung.
That's what I have labeled FG4 here. And then I balance it against the next object. And the process repeats all the way to the top. So I think it would be good for your understanding of torque to study this and make sure you understand just how torques are adding to get you to equilibrium, no rotation. And there's lots of examples of this because every class I did for a couple of years, we put it up on the board. So all you got to do is take a look at all of them and just make sure you understand how torques can sum. The most full understanding we ask you to have of forces and torques is that they're both acting on systems, that they both are causing changes in the system. And just like rotational and linear motion can be looked at separately, you can look at torques and forces separately, and together they can help you solve a problem. Let's look at this one. And this is based off a problem that was in Paul Hewitt's conceptual physics. We got a truck, it's driving out on a bridge. We're trying to figure out what forces are acting on the bridge supports. So we got some numbers. It says the car drives across the bridge. It mass is 1,300 kilograms. The bridge has a mass 2. When the car is 17 meters across the 43-meter bridge, what force is in each of the supporting pylons? So you can imagine that's pretty important civil engineering. You got to design both pylons to be able to withstand the force, which will be changing as the car drives. So in order to solve this problem, you go back and you draw your force picture, your free body diagram. Now you make careful effort to put the forces in the proper places. So I've drawn the car. The car has a weight. It puts a normal force on the bridge, which is basically equal to the weight of the car. That's FNC. FG is the weight of the bridge. FN1 is the left pylon. FN2 is the right pylon. So we know if the bridge is not falling, the forces must sum to 0. In addition, if the bridge is not rotating, the torques must sum to 0. One tricky thing in problems like this is with torque you need an axis of rotation to define your lever arm. Since it's not rotating, you can pick any axis of rotation you want. And the easiest thing to do is to put it on one of your unknown forces. So in the torque equation, that'll cancel out. So we're calling the lever arm this one here. I then look at the torque caused by each of the forces. And these two equations together as a system let me solve for all the things I need to know. So this one is given on the album as well. I think you should study this one too. Look at sigma tau as just another source of information to help you understand a problem. If you're in equilibrium, both sigma f and sigma tau must sum to 0.